Hey guys, welcome to another episode of Physical Science. Today we're going to continue our discussion on waves. Specifically, we're going to be talking about light waves today. We've previously just discussed random, regular old waves. Now we're focusing in on light. So, it turns out that light is not just what we see, like it's not just a light bulb. It comes under this broader category we call in the science world electromagnetic radiation. So here you'll see that we have high energy electromagnetic radiation and low energy electromagnetic radiation. And you'll notice that what's changing is we have different frequencies and different wavelengths. So on the left side over here, that's where we have our highest frequency stuff. So it turns out frequency actually determines energy. So one thing we know about light is that light travels at a certain speed, the speed of light, which is 300 million meters per second or 671 million miles per hour. So very, very fast. But just because it's traveling at a certain speed, that alone doesn't give it energy. What we're looking for here is frequency. So the higher the frequency, the higher the energy. And then we know that wavelength has the opposite trend of frequency. So if we have high frequency over here by our gamma rays, that's where we're going to have super, super short wavelengths. And then if we look at the other side over here, where we have our long radio waves, that's our highest wavelength, and it's also our lowest frequency. A lot of things that you might not think are light are actually technically considered light. Electricity, for example, is technically considered light. Some other things here, and that you'll see electricity from power lines over here. That's some of the long radio waves. So those would be the lowest energy or lowest frequency types of light that we have. Also, higher up in the long radio wave spectrum, we have this thing called a ham radio. Ham radios are used by people, mostly it was used by people in the 70s and 80s as like a hobby. And you could talk to people in different states, or depending on how good your radio is, since some of these radio waves can travel over 1,000 miles, you could talk to people in other countries. So these long radio waves have really, really long wavelengths. That's why they're called long radio waves, versus AM and FM radio waves. Those are considered shorter. So these longer radio waves, you can hear them farther. I know, at least for me, when I'm listening to the radio, my radio tends to cut out if I travel more than like 60 miles away from where it's headquartered at. If you're wondering what radio station I like to listen to, it's 93.7. And so if I travel more than 60 miles away, I can't really hear that radio anymore. It starts to get all staticky and fade out. After long radio waves, we've got AM waves first, and then FM waves. So I don't know if you guys knew this, but AM radio waves, fun fact, will travel longer than FM radio waves will, because they have a higher wavelength. So you can travel further before your AM radio cuts out. But oftentimes FM radio has better signal. Fun fact, AM radio was developed first, then FM came to be. So, cool. Up next, the next higher form of light past radio waves is microwaves. Something you might not know is that Wi-Fi, or the 5G, that is technically a microwave. And it actually shares the same frequency as a microwave oven does. But there are other types of microwaves that are not just a microwave oven. I don't know, I thought that was super cool. I learned that today as I was kind of creating this for you guys. Infrared rays are the next highest. Infrared means below red. So that's how I remember that red is the lowest end of the visible spectrum, the lowest energy, and purple is the highest. Infrared waves oftentimes are used to heat up food or to keep food hot. So oftentimes restaurants will have like little warming stations where the cook will kind of put the food and wait for the server to get it, and they have little infrared lights just kind of keeping the food nice and warm. So they're using light that you can't see to kind of keep the food warm. Also, fun fact, infrared is something that they have in cameras sometimes. So different types of infrared cameras might be able to pick up body temperatures. So if it's really dark outside, you might use an infrared camera to see things that you otherwise wouldn't be able to see. Next thing we have is the visible spectrum. This is light as you know it. It goes Roy to G to Biv, red being the lowest, then orange, yellow, green, blue, and violet, violet being the highest. After you get past violet, you get into ultraviolet. So UV is the next highest. UV comes from the sun, and it's the part of the sun that causes sunburn. So fun fact, regular old light won't get you sunburned. You need UV to do that. Somewhere around UV through X-rays and gamma rays, here we get into radiation that is radioactive. So you probably know UV can cause certain types of skin cancer if you're overexposed to UV waves. X-rays can also cause different types of cancer, and so can this little Y rays. Y, that's gamma there. So gamma rays can also cause different types of cancers. X-rays you'll find in like the medical field when they take an X-ray of like a broken bone or something like that. Usually in those times they'll make you wear like a lead vest just so that the X-rays don't hurt any organs. You can be exposed to a little bit of X-rays and be okay, but extended exposure is kind of what you want to watch out for. It also has to do with power. So not is it only just how much energy do you have, like some of the X-rays, the gamma rays, and UV, but it's also an issue of wattage. So how powerful, which remember wattage is energy over time. So how much energy per time are you experiencing? So yeah, X-rays, fine in small doses, but the more of it you take in, the more damage you can do to your body. Lastly, we have gamma rays over here. Gamma rays you won't ever encounter gamma rays in your everyday life unless you're next to a black hole or a pulsar or a supernova or a neutron star. So gamma rays are some of the most powerful, highest energy radiation we have in our world. And so they only come from some of the most powerful, massive sources. So like if there's a star that explodes, a big enough star is called a supernova when it explodes. So that explosion is going to produce gamma rays. Yeah. So if you're interested in space, you can learn more about gamma rays and stuff. The other thing you might notice about the speed of light is that it's much faster than the speed of sound. The speed of sound is 343 meters per second. So the speed of light is roughly 100,000 times faster than the speed of sound. So yeah, we can go like 10 times the speed of sound now. So we're nowhere near, 100,000 times the speed of sound. That's how fast we need to travel in order to get to the speed of light. So we got a ways to go for manned craft, at least. So here's something that I thought was fun. You might have heard that Wi-Fi is a type of radiation, so it will cause cancer. I heard this a lot growing up. They were like, hey, don't put your cell phone too close in your pocket because it could cause radiation. It could hurt you, and then you won't be able to have kids or something like that. That's totally, totally false. It turns out that cancer is only caused by those ionizing radiation. So ionizing is stuff above ultraviolet. So ultraviolet, X-rays, and gamma rays, if you're exposed to that, then you're in the area where you have to watch out. And even then, it's about power. So it's about how much of this ionizing radiation are you encountering. So it turns out that Wi-Fi is a type of microwave. So it will not ionize. So we're over here in the microwave section, pretty far away from the ionizing section of electromagnetic radiation, the ionizing section of light. So because it's a microwave, it will not cause cancer. Now you might think, wait a minute, Wi-Fi is made up of microwaves. You don't want to stick your hand into microwaves, so Wi-Fi must be bad, right? Well, this is where we have to talk about power. It turns out that a microwave produces about 700 watts of power. So if you put your hand in a microwave, it will burn you because that's the microwave's job, right? It heats out the outside layer by turning the atoms in whatever. So let's say you're heating up pizza. It'll take the water molecules in pizza and just spin them really quickly. By spinning them, that creates some heat, that creates some energy. And that's how you get them to warm up because they're bumping into each other, causing friction. That causes heat. And then the heat just kind of like bumps other molecules until you have hot pizza. So that takes 700 watts of power to do. So that's how you microwave stuff. A Wi-Fi router has 1 watt of power. So that's 700 times less. So even if you like were to take the Wi-Fi router, here's mine over here, and just like stick it to my head, it still wouldn't burn me because it's not enough power. The other thing here is that I've got a little picture over here, and it says power decreases exponentially the closer you are to it. So it turns out that if you're 1 meter away from the source, let's say the router right now, it and I are about 1 meter away. So in that 1 square meter area, I have 1 watt of microwave energy hitting me. Now, if I were to move 2 meters away, the amount of wattage would decrease exponentially. So since now I'm 2 meters away, that means it's a 4 square meter area that 1 watt of power is in. So if my head is in that like 1 by 1 meter area, which it's not, it's a lot smaller than that, but you know, you get the point. Now it's down to 0.25 watts. And I move 3 meters away, now it's down to 0.11 watts. So power is going to decrease exponentially the closer you are to it. So if you stay, well, you don't really have to worry about being close to a Wi-Fi router because the power is too low. But even if it was too high, if you're far enough away from it, you'd be okay. So Wi-Fi will not kill you. 5G, it has the same frequency as Wi-Fi does, has the same frequency as microwaves. It also will not hurt you. So don't be afraid of Wi-Fi. Fun facts. All right, let's talk now about the speed of light. Let's get into what you're going to need to do for some problems here. So speed of light is, well, this is the wavelength equation. We know that velocity is wavelength times frequency. So when we're talking about light, now we're just going to insert a specific speed. And the specific speed of light is 3.00 times 10 to the 8th meters per second. I put this in scientific notation because I wanted to. We're going to be using a lot with scientific notation, so hopefully you remember how to do that. If not, feel free to shoot me an email. We can go over some scientific notation problems. Pretty much you're just going to plug it into your calculator. Always put the whole thing in parentheses. You'll see later as I show it down in your calculator, I put the whole thing in parentheses to kind of avoid any mistakes. So 3.00 times 10 to the 8th meters per second, that's our new kind of standard speed, because anytime we're dealing with light, it's going to be at that speed. And then we're just worried about wavelength and frequency. So we'll give you either wavelength or frequency, and you'll solve for the other one. Here's an example problem below. It says red light has a wavelength of 680 nanometers, which is 6.80 times 10 to the 7th meters. And the question is, what is the frequency of red light? So if I were to have given you this problem last week, you might have looked at this and been like, wait a minute, you don't give us a speed, but now you know the speed of light is 3.00 times 10 to the 8th meters per second. So we can just plug that equation in here right at the top, and then it looks like we're given wavelength and we're solving for frequency. So you'll see here in blue, in green, I highlighted that 6.8 times 10 to the 7th, negative 7th meters is my wavelength, and then blue is my frequency that I'm trying to find here. So I'm going to plug in my wavelength. Frequency stays as f. There it is. Now, to solve this problem, I want to get f by itself. Only way to do that is by dividing this green number by both sides, so I get rid of it. Next step here, there it is. 3 times 10 to the 8th on the top, 6.80 times 10 to the negative 7th on the bottom. Just going to divide these two. Notice that this green number here on the bottom is in parentheses. It has to be, so that I get an answer of 4.141 times 10 to the 14th hertz. If I didn't put this in parentheses, you probably would have gotten 4.41 times 10 to the first, I think, or to the second, somewhere around there, which would totally be the incorrect answer. That's like 440 versus, this is a really, really big number. I think it's like in the quadrillions, maybe, or hundreds of trillions. I don't know, one of the two. Speed of light, hopefully so far we're feeling good about this. Coming up next is another problem. So in this problem here now, Wi-Fi is a type of electromagnetic radiation. It operates at 2.4 gigahertz. Fun fact, that's the same speed that your microwave operates at, or the same frequency that your microwave operates at. So we gave you a frequency. We're asking, what is the wavelength of Wi-Fi? That's the problem. We're going to start with our equation up here, 3 times 10 to the 8th, wavelength times frequency. Now here, we want to know the wavelength, but we're given the frequency. And we know, since we're dealing with electromagnetic radiation, that the speed of light is going to be our speed. So plugging in 2.4 times 10 to the 9th for frequency, then once again, we want to isolate this green guy. So we're going to divide by the blue guy over here. 3 times 10 to the 8th on the top, divided by 2.4 times 10 to the 9th on the bottom. And our wavelength is going to be 0.125 meters. So 1/8 of a meter is the wavelength of a Wi-Fi router. So the Wi-Fi is shooting out waves that are about half a foot, maybe a little bit less, third of a foot, I would say, give or take. Kind of cool. Cool. Last thing I wanted to show you guys is a new equation. It's really simple. This is for a period of a wave. Remember, period is how many times does a wave complete a cycle in a given number of seconds. Yeah, I think that's right. So here we're asking, how long is the period for red light? And we gave you the frequency of red light as 4.11 times 10 to the 14th hertz. So to solve this problem, we know that period t is 1 over frequency. So we're just going to plug in this blue number here for f and divide it. And when we do that, we get 2.27 times 10 to the negative 15 seconds. It's a very short wavelength. Fun fact. Once again here, you're going to want to make sure, see how this number in blue is in parentheses? You're going to want to make sure that you put that number in parentheses when you're plugging this into your calculator. So it's going to be 1 divided by parentheses 4.41 times 10 to the 14th end parentheses. And then you should get this 2.27 times 10 to the negative 15th seconds. So if you didn't, I would just go back and make sure that for both these problems, for the speed of light problems and for the period of a wave problems, that you can actually plug them into your calculator and you get the answer that you see here. If not, it means you're not plugging them in correctly. Okay, that's all I have for you guys here today. So thanks for watching, and I hope you guys have a great rest of your day. Take care.